All right, so welcome back to Calculus 3. So today is lecture 10, and today begins the material that will not be on the first exam. So what we're talking about today will not be on this coming Wednesday's exam. Let me kind of just talk about what's going to happen next week. So Friday, we're just going to continue on to lecture 11. But then next week on Monday and Wednesday, I'm going to be doing a review here in class. So we're going to have some practice exams put up, and then you guys are welcome to take a look at those. And if you have any questions on them, feel free to bring those to class, and I can help you guys out with that stuff. Additionally, Dr. Huang and I are each going to post a video of us like fully completing and explaining one of the exams. So we'll each do a different one, of course. So that will be posted a little bit later as well, probably sometime in the beginning of next week, if you guys want to take a look at that too. Anyways, all right, that's about the announcements. Let's go ahead and get started here. So remember, our itinerary for this class is effectively to mimic Calculus 1, only effectively we're doing it in a higher dimension. We're doing it in three-dimensional space. So consequently, when we were in Calculus 1, since we were in two-dimensional space, we looked at functions involving two variables. We have the independent variable, and then we had one dependent variable right here. But now, since we're in three dimensions, we can afford to have an extra variable. So now we have two input variables and one output variable. So z equals f of xy is going to be our most common function type from here on out. Now, occasionally we'll see things like maybe even like u is f of x, y, and z. So we may see a few things with three variables as well, although this will be a lot more difficult to draw, obviously, because it's kind of hard to draw 4 dimensions on a two-dimensional surface. It's hard enough to draw 3. But we may see some of this and maybe even more variables along the way. Okay, so what we're going to do today is we're going to just go over multivariable functions. So we actually kind of seen that, but in a different way. With parametric equations, we input one variable and then we got out 2 or 3 because we put in t, and then with t, we got x, y, and z. So those are parametric equations. Now, effectively, we're going to do things the other way. We're going to input x and y and then get out a number z. So we've kind of already dealt with the multivariable stuff going on here, but now we're kind of doing it differently. Our multiple variables will be in the domain rather than the range of the output. So speaking of domain and range, just like functions of one variable, functions of multiple variables also have a domain and range. And they mean exactly the same thing that it did for single variable functions. So domain is the set of all x values that you are allowed to plug in to your function. And then the range is the set of possible outputs, all the numbers that you could possibly get out of your function. All right, let's see here. So let's just practice doing this. This usually isn't too hard. Let's try to find the domain and range of these functions. So we have f of xy is x squared plus y squared. And remember, whenever we have f of xy, you could always just kind of imagine that that's z, kind of like how you could imagine that f of x was equal to y back in Calc 1. Okay, so let's talk about the domain, which I'm going to label D. So what numbers are okay to plug into x squared plus y squared? Or let me ask that differently. Are there any numbers that are not okay to square and add together? Yeah, no, we could square any number we want. We can add any two numbers we want. So there's really no restriction on what x and y values we can plug in here. So the answer is going to be all real numbers. But the thing is that we have two sets of all real numbers. We could plug in any number we want for x, and we could plug in any number we want for y. So I'm going to write for the domain R2, meaning I could plug in any x and y value that I want right here. Okay, so then that's the domain. Let's see what the range is going to be. So now, can we get any number we want out from this function, or is there a limit on what we can get out? Yeah, I see some people in the chat saying this. Yeah, 0 or more, that's right. So our range is not going to be all real numbers. It's going to be any z value that's greater than or equal to 0, because these can only be positive or 0. And then, of course, when you add them together, they're positive or 0. Okay, so we have a domain of all real numbers, both for x and y, and a limited range right here. Okay, let's take a look at the next one right here. So let's see here. We're going to find the domain and range of this function here. Oh, can we use brackets? Yeah, sure, you could use brackets. So you could do 0 to infinity. You could also do that if you want. By the way, what would the bracket version of this be? One way to write that is you write what your x could be here, and then you put a cross, kind of like the cross product symbol, an x, and then we have what the y values could be. So you could write it like that as well if you don't want to write the fancy R2. All right, so let's find the domain and range of this guy right here. Okay, domain. So do we have any problems plugging in something for x squared or something in for sine? Are there any issues there? Or can we plug in any number we want? Yeah, we can plug in any number we want for these. So once again, the domain is going to be R2, or if we write it like this, it's negative infinity to infinity, negative infinity to infinity. Okay, let's talk about the range here. Now let's see. So the range for this, oh yeah, we have a question. What's up?
So Professor, like for the previous question, like I was just wondering, can't x and y be some like a subset of irrational numbers like a root 2 or something?
Oh yeah, there's no problem with that. Remember the real numbers contain
Oh
the
yeah, yeah, yeah.
irrational numbers.
Uh-huh.
Yeah, so this means contained or is a part of. Yeah, so there's no problem
Mm-hmm.
with plugging in root 2 or any other bizarre number you
Mm-hmm.
want, like pi or e. There's no issue there.
All right, thank you.
Okay, let's talk about the range for this. So at first we see this x squared here, and we already saw how to deal with that. X squared gives us any positive or at least non-negative number. And then sine can go between -1 and 1 inclusive. So if we combine those two together and multiply them, what's our total range here? Can we hit every number, or is there like a limited amount of numbers that we can hit? All right, chat seems to say every real number, and I agree with that. Because what we could do is we can make any positive number or 0 with this, and then we could plug in either pi over 2 or negative pi over 2 in for sine to flip it negative or positive, depending on which way we want to go. So the range for this is going to be all real numbers if we plug in the correct combination of x squared and y. So it's going to be all real numbers or negative infinity to infinity. All right, so we got those guys. Let's do some more here. Okay. Find the domain and range of this function. Okay, so far our domain's been unrestricted, but I think we might run out of luck for this one. What could go wrong with this one right here? That's right, yeah. So rumor has it that we cannot divide by 0. That's a law you can't violate in mathematics. And plugging in y equals 3 would violate that. So we cannot allow that to happen. So this is going to be all x and y except any x value with y equals 3. Now, it doesn't really matter what this x is. Like this x could be 1,000,000, but if you plug in 3 down there, that's going to be a problem. So this would be how we would say this domain right here. Might 0, 3 work? No, because 0 over 0 is still going to be undefined for that. All right, so this is going to work except for any xy coordinate that has 3 as its y coordinate. Okay, let's talk about the range though. Let me ask you guys this. Do you think we can get any number we want out of this? Seems to be some yeses. Yeah, that's right. Because getting closer and closer to 3 will make this really big, and then getting further away from 3 will make this really small. So we can get any size we want, and then we could maybe make the x be positive or negative, depending on what we wanted to do. So yeah, there's actually a bunch of different ways we can get all the real numbers for this. Okay, so there's all real numbers. Could we use the bracket notation like it's said in the chat? Absolutely, yes. Yeah. So if you want to be fancy with that, it's negative infinity to infinity cross negative infinity to 3, and then 3 to infinity. So let's put some more parentheses there. Yeah, that's totally fine as well here. Yeah, you could do that if you want. All right, let's go to our next one here. I think we're gonna do one more of these. All right, find the domain and range of this function right here. All right, so let's see here, the domain. Now, I think there's something pretty obvious restricting the domain here, and that's going to be the square root. Remember, the input of a square root needs to be greater than or equal to 0. So this means that 1 minus x squared minus y squared needs to be greater than or equal to 0. All right, well, if I add x squared and y squared over here, I get all of the points where 1 is going to be greater than or equal to x squared plus y squared. Now, if 1 were equal to x squared plus y squared, that would be the circle, right? That would be the circle on the xy plane. But now if I have it less than or equal to, what shape is this going to be? Can anyone like verbally describe what this is going to be? If it's less than or equal to? Yeah. Yeah, it's going to be a disk. So the circle is where we have this equal to 1, but then if we go less than 1, we're going to get all of this stuff inside here. So this is called the unit disk right here. So it's the unit circle and then all of the points within that as well. Yeah, filled in circle, that's right. Okay, now let's talk about the range here. So it seemed like in all of these cases, at least one of them was all real numbers between the domain and range, but this will be an exception to that. This will be a case where our range is also going to be limited. What's the limitation on our range here? It's a pretty strong limitation. Yeah, that's right, guys. It's going to be 0 to 1. So we have 0 is less than or equal to z is less than or equal to 1 right here. Reason being is that the smallest this could be inside here is 0, and the square root of 0 is 0. But then the biggest this could be in here, since we're subtracting away these positive things from 1, the biggest we could be in there is 1, and the square root of 1 is 1. So that means no matter what, our output is going to end up being between 0 and 1, although it will include the endpoints because these could be 0 or maybe one of them could be 1 or something like that. So we will include the endpoints for that one. All right. Let's see here. Do x and y fall between -1 and 1 inclusive? Oh yeah, that's a good point. So you guys seem to like the interval notation. However, this right here is not equal to -1 to 1 cross -1 to 1. You might think this might be the case because technically our x could be as low as -1 and as big as 1, and same with y. What shape would this be instead? What would this shape be? Wouldn't be the disk.
A rhombus?
Well, I mean, it would be a square. So it's going to be what's called the unit square. So we have 1, -1, -1, and 1, or -1. I wrote too many negative ones. Too negative. This is what this shape is going to be. Because what this notation means is it can take any combination from something over here and something over here. So you could have like -1, -1, even though that wouldn't show up right here. So watch out for doing the interval notation right here. All right. Let's see here. So in addition to knowing the domain and range of a function, something you also probably learned about one variable functions way back when is graphing them. However, we've already seen that that's going to be much more of an ordeal in more dimensions than it is in just 2 dimensions. I certainly struggle with that, and I've been doing this for quite a while. So we're going to look at some graphs here, but our drawing is going to be limited. And for you guys, you actually don't have to draw anything because again, you're doing everything online right here. All right, so the graph of a function is the set of all points x, y, and z that satisfy the equation. And x, y is in the domain of our f right here. Now, when we made y equals f of x in 2D, This is called a curve. And then now if we have z is f of xy in our current situation, this is going to be a surface. And we've already actually seen several examples of surfaces. We've seen the quadric surfaces. There are several different examples of those. And we've seen planes as well. Those are some examples of surfaces we've seen. But of course, there's the sky's the limit on this. Those are all polynomials, or I guess multinomials. We could also do things with sines, cosines, exponentials, logs, any usual function we want, we can throw them in to a function of x and y right here. All right. So here's an example of this. So maybe this function has a limited domain right here. It's this kind of box in the xy plane. And then here are the different z values that each hover above their corresponding x and y value right here. All right. F of x, y, z a shape? Yeah, it's a surface. That's what I'm saying here. So if you ever have f of x, y, z, okay. That's going to be something that's solid. So in addition to having kind of like a flat 2D surface here, if you have f of x, y, z, that's going to be solid. Yeah, that's right. We're not going to draw that stuff though. And in fact, we'll actually come up with a way of visualizing it, even though we can't draw, although that'll come up in a little bit. All right, find the domain and range for this function. And then once we do that, we're going to describe the graph of f. Meaning we're going to attempt to draw it here. All right, so let's see. So let's do the domain. Let's see here. Are there any numbers that we can't plug into this? You might think that maybe like, oh, I can't plug in any y's to this. But remember, the y value has no bearing on the output here. You could still technically plug in the point like 1, 2. It's just that that 2 would be totally irrelevant to what the output would be. So you can technically still plug in y values, even though it's not showing a y there. So the domain for this is going to be R2 right here. So it's not a 2D graph? No, it will be a 2D graph. Well, we'll see. And then the range right here. So what are the possible outputs we can get for this? Is there some kind of limit on that, or can we get any output we want? Yeah, anything less than or equal to 6. That's right. So z must be less than or equal to 6. Reason being is that we're subtracting off something that's positive or 0 for 6. I don't know if I got to the point in class like in the beginning of the semester, but whenever you are missing a variable, in f of x, y, z, like kind of like we're missing a y right here, then it's going to be a cylinder in the missing variable's direction. And remember, this cylinder is not necessarily like a circular, like can of soda kind of cylinder. It's a shape, it's a 2D shape that's been stretched along a particular axis. So if you're missing, like we're missing a y right here, we'll see when we graph this that we're actually just going to stretch this parabola along y right here. All right, so let's see. So let's try to draw this. Let's just draw this at y equals 0. So at y equals 0, we're going to draw 6 minus x squared. So 1, 2, 3, 4, 5, 6. It's going to be an upside down parabola. Looking kind of like that. And then notice that, so I said I plugged in y equals 0 for that, right? But remember, I can plug in any y value I want, and it's not going to change this. It's not going to change this formula at all. This formula has nothing to do with y. So I could plug in like y equals like 2 or something, and I'm going to end up drawing the same shape. Z is 6 minus x squared. And I'm going to keep doing this forever and ever and ever. So effectively, what I'm going to get is I'm going to get this cylinder that's made up of all of these parabolas. So it's kind of like almost like a tent right here. And it also goes in the other direction as well, the negative direction. So we kind of have like this tent, like cylinder like this, and it stretches all the way left and right forever with y. And then it also, we can't draw it that much, but it keeps going downwards because x can get larger and larger, and this can get very negative. So what does this look like? It's effectively an upside down, infinitely long half pipe looking thing right here. So that's what's going on with this. And remember, this is the key point. I want you guys to remember this because it's easy to kind of freak out if we don't have one of the variables here. But if we don't have one of the variables, that means our surface is going to be a cylinder in the direction of the missing variable. Okay. Let's see here. Find the domain and range of this function and describe this graph. Okay, well, let's see here. So let's do the domain and range first. And then we shall attempt to draw this. All right, the domain. So for this, remember that we have a square root here. So we need the input of this to be greater than or equal to 0. So we need 16 minus 4x squared minus y squared to be greater than or equal to 0. All right, well, I'm going to add these two over here. And then I'm going to divide by 16. All right, so we end up getting this inequality right here. If this were an equal sign, what shape would this be? What 2D shape would this be? Or shape in 2 dimensions? It'd be an ellipse, right? These aren't matching numbers, so it's not going to be quite a circle, but it will be an ellipse. Now, if I have the variables being less than or equal to the number, what do you think this is going to be if it's less than or equal to 1? What was it in the other example? Yeah, it's a filled in ellipse. That's right. And I don't think you can call that a disk properly. Disk usually means cylinder. Maybe we'll call it like an elliptic disk. That seems like a good name for it. An elliptic disk. So it's a filled in ellipse. So that's what this is going to be. So why don't we draw this on the XY plane here? So remember, y goes out at a maximum to the square root of this number. So it's going to go out to 4. And then x goes out to a maximum of the square root of this number. So it's going to be stretching a bit in the y direction like that. All right, why is it filled in? Because of the less than or equal to sign. Because we can input smaller numbers as well, filling in the interior. Okay, so this is going to be our domain right here. This is the domain. It's everything that's going to be in this elliptic disk, or that's what we're going to call it. And then, is it disk or disk? Oh, geez. I think this should be a C disk. I think it's only a K disk if it's a computer disk, right? I'm not totally sure about that. What was that? Oh, so it's disk this way. To be entirely honest, I don't know. Well, you know what it means. You know it says the word disk. So that's all. That's what matters here. All right. Now let's see here. The range. So what is the range of this function going to be? We know it can't be any less than 0, right? Because we have a square root of something. That's never going to give you anything negative. But then is there an upper bound on this? 4, that's right, because at their smallest, we're taking away 0. We have square root of 16. So this gives us 4. Okay, so at most, we're going to get capped off up here somewhere. Okay, now we need to try to attempt to describe this at least, if not draw entirely. So this is going to be most easily described with setting z equal to this right here. Oh, oops, there's an inequality missing. Thank you. All right, so what I'm going to do is I'm going to square everything. So I have z squared is 16 minus 4x squared minus y squared, and I'm going to add the variables to the other side. Z squared plus 4x squared plus y squared is 16. And then once again, I'm going to divide by 16. All righty. All right, so this is where we draw upon our knowledge of quadric surfaces. Which quadric surface is this one, where we have all squares and all positive signs? It's an ellipsoid. That's right. Sort of the general, like the ellipse version of a sphere. So this is an ellipsoid. That's what our shape's going to be. Now, one thing we need to note, though, is that this is the original equation is a square root of this. So this is only going to give us the positive or the top half of the ellipse right here. So we need to remember that this is going to be greater than or equal to 0. We have a domain limitation here. So it's going to stretch up this way, and it's going to stretch up this way. We end up kind of having like this hemisphere, or this dome like this, or a hema ellipse, if you want to call it that. All right, so this is what our figure is going to look like right here. All right, and this is just a reminder for sketching these to use traces if you want. So if you forgot how to draw this, remember we could use traces where we plug in a particular z value and then see what the two-dimensional shape is at that particular z value. I'm not going to go much into detail about this because we're not going to spend an extensive amount of time drawing these, but if you want to draw them, this is probably the best method to do this. All right. Let's see. Let's talk about level curves. So earlier you guys asked me about graphing something like u is f of x, y, z. Now this would need 4 dimensions to graph it most organically, because there's 4 variables of degrees of freedom. But we're already pretty strained in drawing things that require 3 dimensions right here. Like this isn't really the best drawing in the world here. You have to use your imagination to add depth to it. It would take even more imagination to add 2 dimensions to our 2-dimensional paper in order to do this. So typically we don't even attempt to draw them as they are, but we can use something called level curves to still get a good idea of what's going on with these graphs here. So what is a level curve? Given a function and a number k in the range of f, a level curve for this value k is defined to be the set of points satisfying the equation f of x, y is equal to k. And you could kind of imagine this as sort of like a trace. So this is like a trace where z equals k, or maybe u equals k if we have 4 variables here. Okay, and then the collection of all of them together forms what's called a contour map. There may be a more familiar name for this, though, a topographical map. I mean, granted, this is a particular type of contour map, but this may be where you've seen it before. So, you guys might have seen those graphs where you have like elevations of like a mountain range or something like that, and where the lines kind of come close together, that's going to be a steep incline, and then when they're spread apart, it's usually going to be kind of flat. That's essentially what this is, although you could do it for more context than just mapping out topography of somewhere. You could do it for any kind of multivariable function like this. And a topographical map is an excellent example of a contour map. Okay, so let's go ahead and try this out. Describe the surface and the level curves for this right here. Okay, now one thing you need to do before we can draw the level curves right here is the contour map of Florida is just the shape. I think Florida has the smallest difference between its highest point and lowest point in the United States. That's not too far from the truth. All right, anyways, jokes aside, let's just take a look at this. So before we could draw the level curves, we need to know the range of our function. Because for example, for this one, let's say I put I want my k to be -1. What would be wrong with that? What would be wrong with looking at the level curve where k is -1? Yeah, it would be outside of the range. There would be no shape at all because you can't have the square root of x squared plus y squared being -1. So we do need to at least figure out the range before we're going to do this. So our range for this, our range is going to be z greater than or equal to 0, because we can make these x's and y's very large and have a very large square root, meaning we can hit any high value of z we want, but no negative values. All right. So let's see here. So why don't we start with k equals 0? Let's take a look at that. So if I put k equals 0 in for this right here, we're going to have 0 is the square root of x squared plus y squared, or 0 is x squared plus y squared. If we were to graph this on the xy plane, there's only one point for this. The only way we could have x squared plus y squared being 0 is if they're both 0. So technically, this would have to be a little bit of a point right there. That's usually not what they look like, but that's what this one looks like. All right, why don't we try 1? So if we have 1 is the square root of x squared plus y squared, that's the same thing as saying 1 is x squared plus y squared. What curve is this going to be? Yeah, it's a circle. Not just any circle, it's the unit circle. That's right. So we have our unit circle right here. Our unit circle, and then this is where our z is going to equal 1. Okay, let's try 2. Let's see what happens here. And I think after 2, I think we're going to get the idea of what's going on with this. Let's see. Oh, only the top half? Yeah, so this will only be the top half because remember, z is greater than or equal to 0. But we can have negative x and y values because they're being squared away. So it's okay to have negatives for x's and y's. All right, so if we have 2 here, we could square it to get 4. But then this is also a circle centered at the origin, and this time it's going to have radius 2. All right, so we go out to 2. We draw this kind of bad circle. Mostly good except for this. There we go. So this is going to be z equals 2. And I think, yeah, I think we're starting to get the point here. If I keep making my k larger and larger and larger, the contour map for this is just going to be a bunch of concentric circles. So for example, if I do k equals 3, that's going to be, well, all right, it's probably a little bit closer, but you get the point. So that's going to be this right here. And it's only going to get higher and higher as we move away from, well, excuse me. It's going to get higher and higher as we move further away from the origin here. Okay, now what does this look like? What is this? This is the contour map. What does this look like translated to a 3D shape? Because this is actually something that we could draw. If I square both sides of this, I have z squared is x squared plus y squared. This is also a quadric surface. Do you guys remember which one this is? Not quite. It has all squares, but then it has no number 1 like the other ones do. It's kind of like the odd one out with the type 1s. Yeah, I think some people in the chat have it. It's going to be a cone. So this is going to be a cone shape. So we're going to kind of have these lines extending outwards here in each direction. And then we're going to have a circle. Wow, that's an awful cone. But yeah, it's it's a bunch of circles that are kind of expanding outwards as we go up. Now, the elliptic cone with the quadric surfaces also had a negative version, but we're not going to include that because remember, our domain is z greater than or equal to 0. So we're not actually going to include the usual bottom half of that cone or hourglass because we have a restricted range here. All right, and it kind of makes sense here, right? Because the z value keeps getting bigger, and then we have further and further circles away needed for that to happen. All right. Now things are going to get a little bit intense. We have our favorite quadric surface, the hyperbolic paraboloid, aka the Pringle here, or the saddle. We want to consider this, and we want to sketch a contour map of this surface. And they were kind enough to actually draw it for us. If I had to draw it, there'd be no way you would know what it looks like. All right, so we have x and y here. So first of all, let's take a look at what the range can be for this. Is the range going to be limited this time, or can it be all real numbers for this one. Yeah, this one's going to be all real numbers. That's right. Oh, wait. So someone had a good question about the last one here. I want to go back and answer that. So why is the range restricted if when we take a square root, we usually do plus or minus the number? Well, so that's usually when we take a square root. If we start off with a square root, like if we look at the function f of x is root x, then that's only going to be the positive version. If we take a square root of something, then we're going to have plus or minus this. But if they just show a square root that doesn't come from taking from a square, you're only going to have the positive. And yeah, that's right. Sam has the right idea because a function can only return one value. If we had both values, then it would look like this, and it's not actually a function. All right, but yeah, you guys were right about this one. The range is all real numbers, so we don't need to kind of think about that for this one. All right, so let's start doing some level curves here. So since it can be all real numbers, I'm going to do maybe a 0 and then 1 or 2 positive and then 1 or 2 negative. And I think then we'll get the picture. All right, let's do 0. So we're going to have 0 is y squared minus x squared, or x squared equals y squared. Oh, good. All right, so this is going to be, yeah, this is going to be an example of what I literally just said. So if I take the square root of both sides of this, then we have the plus or minus. So this is going to be y is plus or minus x. But if you see just a square root on its own out in the wild without the context of doing a square root like this, then it's not going to have the negative version. All right, so we have y is plus or minus x. So this is y is x, and y is negative x. And along these, z is going to equal 0 right here. All right, let's do k equals 1, see what happens with that. 1 is y squared minus x squared. All right, does anyone recognize what this shape is? What kind of shape is this? It's a hyperbola, that's right. And it makes sense that we're getting hyperbole because we have the hyperbolic parabola here. Now this one has a y as the positive term, so that means we're going to open up in the y direction. And we always open up with whatever the square root of whatever we're dividing y by, which in this case is 1 here. Or sorry, it's always the square root of this number. So I'm going to have kind of going like this. And remember, it goes as an asymptote to these lines here. Okay, so these hyperbole are for z equals 1. Okay, why don't we have a negative version? Let's see what happens with that. So if we have negative 1 is y squared minus x squared, well, in order to get it to the proper form right here, we need to have this be a positive 1. So I'm going to multiply both sides by negative 1. And then we get this hyperbola, which is x squared minus y squared. And this one is going to end up looking like this instead. And now this contour graph is starting to make a little bit more sense here. All right, so this is negative 1, then 0, then 1. So there's a pretty strong gradation for this right here, meaning it's kind of steep right there. And that would kind of correspond to being on like one of the edges of this thing right here. Is this the method for drawing these, just plugging in random numbers? Yep, you just plug in a few convenient numbers and then draw the two-dimensional shapes. Absolutely, there's nothing more to it than that. All right, yeah, as long as it's in the range, you need to make sure it's in the range. Now, if I kept doing this, if I did like k equals 2 or something, I would get more hyperbola, but they would actually start getting closer and closer together as they went along. Because remember, this always starts at whatever the square root of this number is. And square roots of consecutive numbers get closer and closer together. So these are going to get closer and closer together as we go along. It's going to make these kind of ridges right here. All right, so this is what our contour map is going to look like. All right, that one looks kind of cool. All right. So in addition to having level curves, so we could, for both of the examples we just did, we're going to, we were looking at functions where we had z as f of x, y. And for both of them, we actually could have drawn the actual shape in 3D, or at least our imaginative 3D on our page right here. But for other curves, there are sometimes where we can't do that. And for that, like for example, if we have, well, I guess Dr. Huang uses W, I like to use U, but well, whatever. If you have 3 variables right here, when we set this to be a constant, then we're going to have 3 variables left over. And when we have 3 variables defining something, it's going to be a surface. Whereas before, when we set the constant here, we only had 2 variables left, and that's going to just be a curve. So when we go up a dimension, even for the contour maps, we go up a dimension with the shapes as well. So rather than drawing a bunch of lines right here or curves, we are going to draw a bunch of surfaces as well. And this is a bit more challenging to draw because surfaces are in general harder to draw than curves. And here's kind of an explanation of what's going on here. So if we have y equals f of x, that usually resides in R2. This usually resides in R3, and this usually resides in R4. But by using the level version of each one of these graphs, you can cut it back a dimension. And that's not really necessary to do for these guys right here. They're already simple enough. But for these two, you want to use level curves might be a good idea for R3. You definitely need to use them. Level surfaces for R4. It's very hard to visualize without that. Okay, so what we're going to do kind of a 2-step process with a function of 3 variables. All right, so first we're going to find the domain and range of this function, and then we're going to attempt to draw some level surfaces right here. Make sure we have enough time here. All right, we're looking all right. Okay, so let's see here. The domain, well, let's see. So for natural log, we can plug in anything we want so long as it is positive. So that means it's 16 minus 4x squared minus 4y squared minus z squared is greater than or equal to 0. If I add all of my squares over and divide by 16, I have 1 is greater than or equal to x squared over 4, y squared over 4, and z squared over 16. So if I do my algebra right there, this is what I get. Okay, now if this were an equal sign, so we're going to go through this reasoning a 3rd time now. If this is an equal sign, what surface would this be? 3 positives and all squares. Yeah, it's going to be an ellipsoid. That's right. So this is an ellipsoid. But then if we have the less than or equal to sign, what's that going to be? How would you describe that? Yeah, it's like a solid version of it, right? Someone said a blimp. Yeah, it's kind of like a filled, well, actually not a blimp. Blimps are hollow on the inside, but like it's filled in. So this is a filled in ellipsoid. All right, so we can't move outside of this ellipsoid. Okay, now the range here, let's see what that's going to be. So at best, all of these could be 0, right? We're subtracting 0 away from this. And that's going to give us natural log of 16. And then, so that's going to be our upper bound. That's as big as we're going to be able to get. And then on the other hand, as the inside gets closer to 0, what's log going to do? It's going to go down to negative infinity. So this time we have a much, we have a limited range, but it still goes to infinity, at least in one direction right here. Oh, oops, I'm used to writing z's, sorry. It's going to be u or w if you want. Either one's fine. How's it negative infinity? Because the limit as x goes to 0 from the right of log of x is negative infinity. So as our input gets closer to 0, the output needs to be negative infinity. All right. Then we have all this space. What we're going to do is we're going to characterize the level surfaces of this function right here. Okay, so let's see. So we have u is natural log of all of this stuff, right? Okay. So let's see here. What I'm going to do, I wrote down a way of doing this that was somewhat effective. Let's see. Okay, so here is our function in terms of all four of its variables, the one dependent and then the three independent here. Oh, oops, sorry, you're right. I've been making a lot of little mistakes today. This should be natural log of 16 or 4 ln of 2 if you'd like to simplify this. All right, so back to this. We have all four of our variables here. Now let's think about this. So if we have a larger u value, that's the same thing as having a larger inside of our natural log, right? Because the bigger we make the inside of the natural log, the bigger the output's going to be. Okay, now if we want to have a larger inside of our log, that means we're going to make x, y, and z be smaller. So if x, y, and z are going to be smaller, then this is going to be a smaller ellipsoid. So what's going to happen? What does this reasoning tell us? If we have our level surfaces right here, all of these level surfaces are going to be ellipsoids that look like this. So all these ellipsoids, so we're going to start here at 0 if all x, y, and z are 0, and then we're going to have u is what? What is u going to be at the origin right here? If x, y, and z are as small as possible at 0. We're going to have ln of 16. That's right. So if we plug in 0 for all of these, meaning we're at the origin here, we're going to have u is ln of 16. Okay, now as our ellipsoid gets bigger, and I'm going to just try to draw like a generic sphere. I don't think we have enough time to really draw a full thing here. But the bigger my ellipsoid gets, the lower my u is going to get. So we're going to have, maybe this will be like u equals 0. And if I have a bigger one right here, it's going to be u is like -1. And then when I draw the full ellipsoid, when I draw this ellipsoid right here, once I draw the full sized one, let's see, it's going to be, oh no, it's only 2 in the x direction. 2 in the y direction, 4 here. So when I draw the full sized ellipsoid, like this is going to be -infinity. So effectively, what we're doing is we're having a bunch of concentric ellipsoids. We have a bunch of these surfaces kind of contained within one another, similar to the way back in the earlier example, we have this right here, except everything's kind of propped up a dimension right here. So everything's propped up a dimension. So rather than having concentric circles or ellipses, we're having concentric ellipsoids. We have a bunch of these kind of blimps or shells containing one another. And the further out we go, the bigger x, y, and z get, the smaller the inside of my log gets. And the smaller the inside of your log gets, it gets more and more negative. So that's why we have our level curves being negative as we move all the way out. So it's like a Russian doll. Yeah, that's right. That it is kind of right. It's like a Russian nesting doll, and the bigger outermost one is -infinity, and then we get more and more positive till we get to the middle tiny one, which is log of 16. So that's what that one's going to look like. Don't worry, we're not going to do too many level surfaces here. I wanted to expose you to what this is, and I want to illustrate just how difficult it is to represent visually functions with 4 variables here. We're not going to do extensive stuff with this, but it is something you should be exposed to here. Let's see here. How are we doing on the time? All right, we got 1 minute left. Now this next part, I already kind of yeah, don't worry about this for now. This is an exposition. So I already kind of went over in the beginning of the semester how we should always try to, when we encounter a new concept, to liken things back to Calculus 1. And that's what we're going to be doing with this section. This section is going to end up being all about derivatives. And kind of like how we had first and second derivatives here, kind of like how we had linear approximation here, or tangent lines, we had a chain rule here, and then setting derivatives equal to 0, we're going to have matching things over here. And we have this kind of weird symbol for our derivatives, which I'll talk about once we actually get there. But remember, this page is essentially just a reminder, whenever we encounter a new concept, it's extremely likely that there's something we already did in Calc 1 that's going to be similar to that. So I want you guys to kind of keep this philosophy in mind when we're learning about derivatives, which is what we're going to be doing over the next few lessons right here. All right, that about does it for today right here.